Okay, so this is chapter 12.2 on ionic bonds, and a lot of this is going to seem like a review. We're just applying some of the things that we've learned to ionic bonds. Remember, those are between metals and nonmetals, and that's when we're giving and taking electrons. So we're giving electrons from metals, and then the nonmetals are taking the electrons, and that's an ionic bond. So we will be looking at electron configurations, which is where we were in the last chapter looking at those different suborbitals, the 1s, 2s stuff. And we're going to be applying that to giving and taking electrons and looking at where the electrons are going. And then we'll also be looking at formulas again and how that relates to formulas and their structures. And so this is also just a review. When ions ionize, when they become charged, they become like noble gases. So for example, when you have like sodium, which is in group 1, which has 1 valence electron, if it loses an electron, it becomes positively charged. So it becomes a 1 plus cation, and sodium is going to become like neon, I think. Let me find a periodic table. So here is sodium. I don't have noble gases on this one, but when it loses that 1 electron, because all of these have 1 valence electron, then it's going to lose a shell and it's going to become more like neon, which would be right here, number 18. So they're going to get noble gas electron configurations. And we kind of saw that in the last chapter. And then we see this happening also with group 2. They have 2 valence electrons. So when they lose those 2 electrons, they become 2 plus, and they're going to become like the noble gas that's kind of before them. So if we go up to like magnesium here, it would lose 2 electrons, and it would be, we zip behind here, it would go over to neon. So it would be around the same size as neon, and it would have the same electron configurations. And then same thing here with aluminum. It's in group 3. It has a 3 plus cation, and it would also become like a noble gas. And then these nonmetals have, so they're in group 6 or 7. They either have 2 electrons to give, or I'm sorry, to gain. So they're going to become a 2 minus charge and become an anion. Or in group 7 here, they're going to have 1 electron to gain. So they're going to become a 1 minus charge. And they are going to get bigger. They're going to have the same electron configuration as the noble gas after them. So like fluorine here has 7 electrons, and it's going to gain 1 electron and have an electron similar to neon. Chlorine will have, will be similar to argon. Oxygen will gain 2 electrons, and it'll be similar to neon. All right. So here's what that looks like. Lithium here, this is the electron configuration. It has 2 electrons in the first shell, opposite spin, and then 1 electron on the second shell for a total of 3. But it's going to want to lose this electron, and when it does, it'll become more like helium because it'll have 2 electrons on its outer shell. And then beryllium will also lose these 2, and it'll become more like helium. And boron will also lose these 3, and it'll become more like helium. And then if we move up to carbon, this is where we might gain 4 electrons. We're probably going to be sharing. And so this one will, if it gains 4, it'll be like neon, which is down here. So it's going to be sharing those electrons and gaining them. Nitrogen is also going to gain 3 electrons, 1, 2, 3, and it'll also look like neon when it's sharing those. Oxygen's going to gain 2 electrons. Oxygen will probably be involved in ionic bonds or covalent bonds. And so it'll either share or gain, and it'll look like neon. And then fluorine here, same thing, it's going to look like neon. And this is how their sizes change when they become ions. This silver one up here, if we start at the top left, this is lithium. And then when it loses that electron, it gets smaller and it becomes a little bit more like helium. It's going to be a little bigger than helium, but close to the size of helium. And you can see they get smaller. Here's sodium. This is normal neutral sodium. This is the stuff that blows up in water. It's a soft metal. You cut it like butter. We did that in class. And then when you lose that outer electron, it's going to be smaller. So here's the size difference. And then you see the same thing with potassium and with rubidium. Beryllium here, this is the original, zero charge. When it loses 2 electrons, it becomes Be2+, and it becomes smaller. So you can see all of these are getting smaller. They're losing shells, they're losing electrons, and they're becoming positively charged. Same thing with these in group 13. Boron is going to lose 3 electrons, so it's going to become a lot smaller. And you can go all the way down. Now these blue ones on the right side are different. So this oxygen here, this is the normal oxygen, it's stable. And then it's going to gain 2 electrons, and this is what it's going to look like. It's actually going to get bigger. It's not gaining any shells. So we see here oxygen, we're not adding any shells. We still just have our 1 shell and our 2s shell, but we add these 2 electrons and it makes it fluffier because that nucleus is not able to hold it, hold those shells to it as tightly. This right here, this silver, is not the nucleus, right? This is just our neutral shell of our oxygen atom, and then this is the shell of our oxygen ion, our 2- ion, just showing that it's bigger. And then we see the same trend here, and we see the same thing with our group 17 halogens. We start out with a smaller fluorine, and then when we add that 1 more electron, it's going to get a lot fluffier because the nucleus way deep inside there is not able to hold that 1 shell as tightly. And so again, this is what we're looking at. We're seeing here that sodium has 1 valence electron, and it's going to give it to chlorine, which is missing 1. Chlorine has 7 valence, it's missing that 8th one, and the sodium has that to give. So sodium's going to lose this outer shell, and chlorine is not going to gain a shell, but it is going to get fluffier because this nucleus only has, what, 17 protons, and now it has 18 electrons to hang on to, so it's just not able to suck that outer shell as tightly, so it's going to get fluffier. And this is another view. This is basically our electron configuration, but it's in the form of orbital diagrams, right? And the orbital diagrams that we've written before have been in a straight line, but now this one is in this setup where it's showing those energy levels. Remember, 1s is the lowest energy level, and then you go 2s, 2p, 3s, and 3p. So we have sodium over here, and here's that 1 electron, same as this one, that we're going to give. And then here we have chlorine, and we have that same setup, but then this last little spot here would be that missing 8th electron in that diagram. And so what we're seeing now is we're seeing that we're going to take this electron from sodium and we're giving it to this spot right here in chlorine. And basically we're just kind of keeping track of where those electrons are coming from and where they're going and which electrons are actually bonding. So we're seeing the electron from the 3s shell is bonding here with the 3p shell of the chlorine. And here's another look at it. So this is that same picture. We have that 1 sodium electron, and it's being given to the chlorine. And this is an ionic bond, metal, non-metal. And then here's another look. These are our Lewis dot diagrams. We have that 1 sodium electron on the valence shell, and it's going to be transferred over here. And then here we see the result, a positive sodium ion and a negative chlorine ion. And then this is showing the same thing. We lost that shell, and we've gained an electron here. And then down here we have the electron configuration. So here's sodium again with that 3s1 on the outer shell. And here's chlorine with the 3p5. So on that outer shell right here, the 3rd shell, we have a total of 7 electrons. We have 2 on the s shell, and then we have 5 on the p shell when we could have 6. And then we're just taking that 3s electron and we're moving it over here. So now sodium does not have anything in the 3s shell, and now chlorine has that 1 electron in the 3p6 shell. I'll kind of sit on that for a little while if you want to write that down. Remember, you can always pause it. So hopefully that ties it all together, all these different ways that we've learned how to track where these electrons are, and now we can use that to figure out where they're going when we're bonding. So finally, when we are bonding these metals and nonmetals, they actually form this crystalline structure. They become crystals. So you can think of like a salt crystal. And if you look at salt really closely, it's actually a perfect cube. So here we have a positive sodium ion and a negative chlorine ion, and they are bonding together. The cation is going to be smaller because it lost that outer shell. It gave electrons. And then that anion, the nonmetal, is going to be bigger because it gained electrons. So it makes it get fluffier. And these crystalline solids are hard but brittle. So you can take a hammer and you can smash them, but they're also really hard. And this is what we're looking at. If you were to hit like a salt crystal with a hammer, you're going to like dislodge these bonds, because then it's no longer like chlorine, sodium, chlorine, sodium. You're going to get them out of whack, and that's what's going to cause it to like crack or fracture. And this is what we see with all crystallines. There's a lot of other kinds of crystalline solids, any kind of ionic bond. We've messed with a lot of them in labs. We've used them a lot. Most of the labs that we've done where you made an aqueous solution, we're using crystalline solids. So you've seen a lot of different colors and types. The most common one we probably see is table salt. And the other interesting thing about these crystalline solids is that they're also really soluble in water. And that's because when you dump this in water, water is polar, which we learned in section 1 on Thursday. The positive part of water, the H's, are going to surround the Cl, and they're literally going to rip it apart. And then the negative part of water, the oxygen, is going to surround the sodium, and it's also going to rip it apart. So that's why salt is so soluble in water. This last part here is on lattice energy. Lattice energy tells us how much energy there is stored in a bond. So you can think of a lattice, like you might have seen lattices in gardens, and they kind of have this structure like this, and you can grow vines on them. They're usually like a wood structure, kind of a crisscross. And so this is showing basically the energy in these bonds between like the sodium and the chlorine. And the amount of lattice energy depends on how many electrons we're moving, how many electrons are being given and taken. So like lithium and fluorine, and some of these in like this neighborhood, they only have a charge of +1 or -1, and so they have a lattice energy of like around 600 to 1,000. So you can see this chunk right here. That area is in that range of like 600 to 1,000. But then when we start trading, when we start donating more than 1 electron, so beryllium, magnesium, calcium, those are giving up 2 electrons, you can see that our lattice energy has increased. And then aluminum here is giving up 3 electrons, and you can see here our lattice energy is like 5,000. With these different anions, we're kind of keeping that same neighborhood of like these 2 and 3,000s and the 5,000s for aluminum, and we're only accepting 1 electron for each of these. So like for aluminum, you're giving up 3 electrons. You would need 3 fluorines to give those electrons to. So your formula, if you were to bond those, would be AlF3, which we've learned before. You just crisscross those oxidation numbers. And then over here with oxygen, if we have 2 electrons to give up, these 2, like lithium here is only giving up 1, and then oxygen's going to give up 2, and your lattice energy goes way up because you're transferring more electrons, and you're going to need 2 lithiums here to give to this oxygen. And so your formula with those 2 would be Li2O. So you can kind of predict that, and you can think about that as you go down. Sodium would be Na2O, because you need 2 sodium ions to donate 2 electrons to the oxygen, and same with potassium. And then beryllium here, that's going to donate 2 electrons. Oxygen's going to take 2 electrons. You have a higher lattice energy. You're transferring more electrons, but you're only going to need 1 of each. So it's going to be BeO, because they're both transferring 2 electrons and they're satisfied. Same thing with magnesium and oxygen. It'll just be MgO. Calcium and oxygen will be MgO. But then look at this huge jump here in our aluminum. when we're bonding that with our oxygen, you're actually transferring 6 electrons there. So that's why we see such a big jump. And our formula then would be Al2O3 to satisfy those 6 electrons. And if you have trouble, if you're not following that part, just let me know and I can try to explain it in a different way. And then these are some other ions that we've seen the names of and the formulas, but probably not the structure. So this one might look familiar. Ammonium is NH4+, and that's been one of our polyatomic ions that we've named and bonded with. Our nitrate ion should look familiar, NO3-, and then SO42- and PO43-. And so this is what they actually look like. Like on this one, you have your P in the middle, your phosphorus, and then you have your 4 oxygens. And overall, this whole monster has a 3- charge. And then same thing here with the sulfate, you've got your S in the middle with 4 O's, and then a 2- charge here all over. And we will learn how to do that later. Nitrate here has an N in the middle, and then 3 oxygens, and then it has an overall 1- charge. And then here, ammonium has an N in the middle with 4 H's and an overall plus charge. Okay, so that's kind of more of this Lewis structure that we'll look at on the next lesson. So for chapter 12.2, you need to go in your book, and the questions for that are on page 439, and you need to do 1 through 7. And please email me if you have questions.